Hello everybody. So here we have a box which is pulled to the right so that it accelerates across the floor. Thusly. See it speed up, right, as it goes to the right? Well, what variables affect that acceleration? The acceleration that we normally measure in meters per second squared. Right? Like, what could we change about this situation that might change the acceleration? Well, one of the things that we could change is we could change this force right here, right? We could pull more or less. And some of you might be saying, well, we could also do something like maybe change the amount of friction, or we could change the angle of the floor. And all those things would factor into the net force. Okay, so I'm going to use net force here because it takes a net force to make something accelerate. Right, so whether there's friction or not, or an angle or not, what's important here is the net force. And we could change that, and that might change the acceleration. What do you think we could change maybe about the box? Well, sure, we could change something fundamental about the box. Let's say like its mass, right? And that might affect it. So even if we pull it just as hard, right? If the box is twice as massive, is it going to accelerate the same way? So here's three variables that seem to be related to one another. And you'll notice here that we are measuring acceleration in meters per second squared. We are measuring mass in kilograms. And we are measuring net force in newtons. Now, you might remember that the newton is the SI unit of force, the International System of Units unit of force, metric system, if you will, plus. The newton, because it's named after Sir Isaac, is a capital N as a symbol. Now, back when I first introduced the newton to you, this was back during the Force of Gravity lab a couple of units ago, and at that point I said, well, let's think about what a newton actually is in terms of a unit that we're more familiar with, the pound. And we said that 1 newton is about 0.2248 pounds. It's a little less than a quarter of a pound. So a newton is a fairly small unit of force, right? A little less than a quarter of a pound. There's about 4.448 newtons in 1 pound. But back then I said we did not have the physics yet to be able to explain why was a newton this size. Right? Why did scientists choose a newton to be a size that ended up being 0.2248 pounds? I mean, obviously they didn't say, let's just make it this much. That doesn't make any sense, right? There's got to be some physics behind this. So that's what we're going to try to figure out in this little activity that we're going to do today. Okay? Is why is a newton a newton? So the purpose of this activity, as it'll say right at the top of your lab sheet, is to determine the force in newtons required to accelerate a 1 kilogram cart at 1 meter per second squared. And from that, we're going to be able to define a newton. Okay, so again, we're going to try to figure out what 1 newton means by kind of figuring out what it does. Right? How much force does it take to accelerate a 1 kilogram cart at 1 meter per second squared? So this is called the definition of a newton activity. Okay? Now, to do this, we're going to have to use some fairly complex equipment. And our equipment looks similar to this little video I'm going to show you here, which is from Pivot Interactives. We don't quite have their equipment. They're using an air track here to reduce friction. We're going to use carts on tracks. Right? But you'll notice that a modified Atwood's machine is composed of this cart with a string that runs over. It's hard to see in here, but it's a massless, frictionless pulley. We actually have these plastic pulleys that are really, really low friction when you get a look at them. And then a mass hanging off the side. Okay, it's called a modified Atwood's machine because it's named for a contemporary of Isaac Newton's named Sir Robert Atwood, who studied them. A full Atwood's machine has masses over a pulley which both go up and down. Okay, so there isn't one on a horizontal surface like this, or a cart on a track or something. Okay, this is a modified Atwood's machine because one of the carts on a track. Okay, and down here we can change things, but we're not going to change things. We're just going to leave them here. But I just want you to watch what's going on here with the cart. Okay, so I'm going to play this video, and I want you to watch what happens when it's released. You see it accelerating as the mass falls? Right? So the cart accelerates because the mass falls. Right? The mass has gravity pulling on it, and that's accelerating the system. And that's what we're going to do in this lab, or that's the kind of apparatus we're going to use in this lab, okay? And I will explain to you how we're going to measure everything, the force, the mass, and the acceleration of the cart. We're going to get really fancy in this one and go very high tech, okay? But I do want you to watch it again for one particular reason here. I want you to look at what happens when, after the masses get to the floor. I want you to watch what happens to the cart. So here it goes. Masses are falling. Cart's accelerating. It's getting faster and faster. Masses hit the floor. You see what happened? So as soon as the masses hit the floor, they stop pulling on the string. Well, once the string goes slack, right, then the string stops pulling on the masses. And so what kind of motion did they look like they had? Let me show you that last little bit again. Let's see here. Let's go to about here and start her up. Yep, here it comes, right? Look pretty constant, right? So after the masses hit the floor, well, now there's no forces. And since there's no forces, it moves constantly. Okay? So, we're going to use a little modified Atwood's machine. This is my little schematic of it. It's a cart, which we're going to call A. So this is our smart cart. It's called the smart cart because we can measure lots of things with it. Okay? And this B is the hanging mass. This is our massless, frictionless pulley that we can kind of ignore because it's massless and frictionless. But it does help us control things. And so now what I want to do is to look at why things move the way they do and how we're going to measure everything. So let's do a quick little force diagram of our cart, because that's what we're really worried about here. Right? We want the cart to be 1 kilogram and accelerate at 1 meter per second squared, and then measure how much force that takes. So what forces act on the cart? Well, of course, there is the force of gravity, right, which is acting on the cart, which is A, which acts down. The cart is being supported by the track, so there's a normal force acting up, perpendicular to the track. How big do those two forces going to be, do you think? Well, yeah, they're going to balance out, right? They're going to balance out. How do we know they balance out? Well, in the past, we would say because it has a constant velocity, vertically, right? Up and down, this cart just moves horizontally. So vertically, it doesn't move at all. But now we can be a little more complex because we now know that what's it not doing if it's not moving, right? It's not accelerating. So we can upgrade our talk here, right? Instead of saying it's got a constant velocity, we can say no acceleration. It's going to be common language in this unit, all right? So no acceleration, right? When there's no force acting on it, when the force is balanced. Okay? But that's not all that's acting on the cart. The cart also has a force of tension acting to the right. The string is pulling on it. Now, in our movie, that was it. Right? We could assume because it was riding on a little cushion of air that there was basically no friction. And because it just sat there until it was released, right, we can assume that it didn't have any angle, to the track, right, or anything like that. But that's in this perfect little movie world that we were looking at there. What about in our actual equipment? Well, our actual equipment, we have wheels on a track, right? So there might be a little friction. And unless we're careful, there might even be some angle to the track. But I've done something clever, okay? When you get back there, if you give your cart a little push, it's going to move constantly down the track. This is taking the string off, right? So no string at all, just the cart, right? Give it a little push, it's going to move constantly. Well, why does it move constantly? Because I did something tricky. I balanced these out, okay? What I did was I actually angled the track so that it's actually tilted down a little bit, right? I picked up this end. You'll see some paper back there. Please don't move it, okay? I raised the track up so that the angle of the track was balancing friction. Because, since they're balanced, we can ignore them in the lab. So this is kind of the neat way that we're going to make our lab in real life work like the very fancy air track in the movie that we saw. Okay? And this is only true if when you give it a push, it moves constantly. And you can test it because spend a lot of time making sure all the tracks work. If you think your cart accelerates on its own, call me over and we'll fix the track, right? In case somebody in another hour messed with it. But we should have this set up so that these are the only forces we have to worry about acting on the cart. We can ignore any friction in the angle of the track. Nice. So, what's providing the net force in this case? Well, look at the force diagram, right? It's the force of tension in the strain. And thankfully, there's several things the cart can do. One of them is that it has a force probe in it. And this is a little, you'll see when you get back there, there's a little hook over here, right, that we can attach things to. And the hook is screwed into the force probe. And the string is attached to the hook. Right? So the force probe is going to be able to measure the force of tension. I'll show you what that looks like in a moment. Okay? But the other cool thing, if you pick up and look at the bottom of our cart, it has a fifth wheel in the middle of it. Okay? There's this wheel in the middle. Very springy wheel. Okay, trying to play with it too much. But that wheel is actually really cool because what it does is as the wheel turns, as the cart moves, it measures the turning of that wheel. Right? There's a sensor inside of the cart that you can't see. And it's measuring the turning of that wheel. And it's converting it over to the position of the cart. Like how far the cart had to move because the wheel's spinning. You with me? So it's using the turning of the center wheel to figure out how far the cart is going. And so that way we can replace a motion detector that we've used earlier in the year with this special cart. All right? And of course, it's all Bluetooth, which means there's no wires running from it. It'll go right into the Bluetooth adapter onto the computer and right into our graphical analysis program. All right? So what's this going to look like? Well, let me open up a sample here. This is a run I did a while ago. Okay. So here we have two graphs, and there will be instructions for how to set everything up on your table. Okay, for how to get this set up, you've got to register your cart to graphical analysis, all right, because there's a bunch of carts in this room, so your computer needs to know which cart is yours. There's instructions for that. And then you need to tell it what you're going to measure. Okay, you need to turn the force probe on, and you need to turn the wheel on. It defaults to being on. And then you're going to set up two graphs. The top one is a graph of velocity versus time. So basically, it's actually doing position versus time and then converting it over to the velocities. Remember how we did that by taking 3 points and then the velocity was the slope of the tangent line, right? Well, the computer's doing that inside of it, right? It's doing it really fast so that it'll look like it's real time. Down here, you want a graph of force versus time. So this is the force acting on the cart. Okay? Now, first off, let's talk about the velocity time graph up here. And you'll notice there's kind of some distinct parts to it. What's going on here for the first couple of tenths of a second? Well, this is a velocity time graph, so it's not moving yet. So maybe there'll be a collect button up here, right? Maybe you've hit the collect button, but you haven't let go of the cart right away. That's fine. But it's not part of what we need. We're trying to figure out acceleration. What's happening over here? Well, this is where the cart is coming to rest. And please catch your cart at the end of the track. So don't let the cart run into the pulley. Okay, these are very expensive carts and pulleys. So catch the cart, have somebody designated to do that. Okay? So we don't want this part, right? And you might see up here a little flat part. Now, depending on your setup, this might be a little bigger, a little smaller. Okay? What's going on there? Well, you remember the movie we watched? Right? If it's flat on a velocity time graph, that means it's basically going at a constant velocity. And we saw what happens there. This is when the hanging mass hits the floor and stops pulling on the string, and the string stops pulling on the cart, and so the cart moves constantly. So we don't want that part. We only want the part where the cart is accelerating. That's the diagonal part. How are we going to find the acceleration? This is a graph of velocity versus time, so how do you see the acceleration? It's the slope of the graph. So again, if we select the part of the graph we want, click and drag over it, get a good long run, make sure you're not getting the schmutz over here when the masses have hit the floor or you've caught the cart. Don't get the schmutz over here where it's just getting going or before you let it go. And then we come down here, go to apply curve fit, linear, and there we go. Here is the slope of the velocity time graph. At this point, the cart was accelerating at about 0.6326 meters per second squared. And I can even make that a little bigger if we want to see it. There we go, right? So it's 0.6326 is what it's going at here. Again, all we had to do was click and drag over the part of the graph we want, the diagonal part where it's accelerating. Apply the curve fit, and the slope is the acceleration. Boom. Nice, right? Now, in this lab, and I'll have this on the sheet, and all of the instructions, by the way, are on your lab sheet as well. Right? You're trying to get this cart to accelerate not at 0.6325, but at 1 meter per second squared, as close as you possibly can to 1.00 meters per second squared. So if the trial's not good, you just do a new one, right? And you have to go through these same steps to see the acceleration. But eventually, you're going to get it to accelerate at 1. And once it accelerates at 1, then you're going to want to figure out how much force was applied. Okay? So let's take a look at the force time graph. One weird thing about it here, you might notice that the scales don't match on these two graphs. Like this is 1 second over here. This is 1 second way over here. If you double click on the graph or push this button, which is auto scale, zoom to fit all data. All right, either way. All right, see how it auto scaled and now the axes are the same, just kind of nice. It might default that way, it might not. Okay. Well, notice that there's kind of several parts to the force graph. There's this part, which is basically horizontal, so it's constant. But notice if you match up here, that's before it was accelerating, right? So this is how much force the string is applying to the cart when you're holding on to the cart to keep all the forces balanced. This is not the force that the string is applying while it's accelerating, right? That's this part of the velocity time graph, and so it is this part of the force time graph. You with me? Now that's a horizontal line as well, but you do notice it's bouncing up and down a little bit. All right, so we got a lot of data points in here, a ton of data points in here, right? So what we can do then is, instead of looking at, like, we could just click on the graph and look at one point, we can see roughly how much it is, but, you know, why? Instead, we can pick a nice flat part of the graph, go in here, go to statistics, and then look at average or mean, 0.490 newtons. That's the average force that's being applied. With me? Again, this is all on the sheet. Most of the time, you're going to be futzing with the velocity time graph to try to get your acceleration to be exactly 1. But once you do, then you will be able to do the force, right, and see the mean force here by selecting these things. Okay? Again, you know, you can see here that we basically selected the same part of both graphs to look at, right? And we didn't pick the schmutz before you let it go, and we didn't pick the schmutz after you caught it or after the masses hit the floor, right? It's just while it's accelerating that we want to look at. Okay? Pretty extensive instructions to get this stuff set up. So if you're having trouble, call me over, right? We can set everything up, but there should be some instructions right on either your table or additional instructions on your lab sheet. Okay. Your cart should be set up right now to be exactly 1 kilogram, within a gram of that, all right? We were, you know, really precise. Just to convince you that it is, you can take the string off it, right? And take the cart over to the scale. It's in the back of the room, and put it on there, and it should be basically a kilogram, all right? If it's more than like a gram away from that, show it to me and I'll fix it. Okay, or call me over to the scale and we'll fix it. It should be dead on 1 kilogram if no one's messed with it, all right, from 1 hour to the other. Then I want you to put about 110 grams, 0.110 kilograms, on the end of the string, on the mass hanger. So I want you to put that on here. You've got a box of masses, the blue box, that are back on the tables. All right, there are all sorts of masses in there. They go anywhere from 100 grams at the high end down to a single gram mass, the smallest ones of them. Be careful with these masses. All right, this box is pretty expensive because these are brass masses. They have their mass written right on them in grams. All right, please try to keep all the masses organized. At the end of the hour, I hope you set everything back up the way that you found it, right, so that the next hour is ready to go. So put about 110 grams on the end of the string. Okay, for now. It doesn't really matter if it's exact or not. We're just trying to get you close. And then if you put it on there and you run a trial and it's not accelerating at 1 meter per second squared, well, how can we make it accelerate faster? What could we change, and look at our force diagram, that would change the net force and therefore the acceleration? Well, yeah, we got to change the force of tension in the string. And how can we change that? Follow it over. Right? We could do that by changing the hanging mass. So again, you've got your box of masses. You can keep adding masses to this until it makes it accelerate at 1 meter per second squared. That's the lab, people. Okay. Now be as precise as possible, down to a gram if you can. Take your time, please. This is not something to rush through. Okay. If you put another gram onto your hanging mass, it should go above 1 meter per second squared. You take one off, it probably will be just below 1.00 meter per second squared. Try to get it as close as you possibly can. Okay. It's a whole reason why we're using this super complex equipment, right, is so that we can get very good results. Once you get it accelerating at 1 meter per second squared, then you're going to do that thing I showed you to find the average force and see how much force it takes. Right? As you'll see on your lab sheet, you're then going to go onto the schedule doc and you're going to put that into a Google Doc, however much force it is, so that we can average everybody's up and see what that force was. And along the way, hopefully, see if we can come up with the definition of a Newton. Why is the Newton the size that it is? So be careful with the equipment. Ask questions if you got them. It's kind of a little complex of a setup, but it works really well once you get it going.